Okay, good morning, and I really appreciate your cooperation this morning. And it's not easy to get up early, right? I guess that most of you, this is your first time to attend the 8:30 class in KAIST. Okay, good. So I want to start with some basic theories, as I mentioned, because in order to fully understand every, element in the regression result report, we need to understand a certain. It's not too much theory. It's about some technical details. And I think that I talked about the logic underlying the regression analysis. So let's say we have X and Y, and the actual relationship is like this. And then in order to express the relationship in a linear format, we need to have something like this: Y alpha plus beta X. But as you can see, when there are some actual data points, you cannot have linear relationship by connecting all these dots. So somehow we have to make some sort of judgment about what might be the best linear relationship that describe the actual relationship between these two variables. So let's say, okay, I want to have this. So this is my estimate. Let's say y hat. Y hat is my estimate, and this is true values. So as you can see, the estimation is not always the same as the actual relationship. In other words, sometimes we have some differences like this, and sometimes we have some differences like this. So I think that the given x, sometimes let's say that's y, actual value, and that's our estimation y hat. So when we use this regression line to describe the relationship between this, independent variable and dependent variable, we make some mistakes. For example, let's say y minus y hat. And if we want to express this data point with y minus y hat, and we call that as error. Okay? We are making some errors. So I mentioned that how we can decide this alpha and beta. We want to decide alpha and beta in a way to minimize, some sort of sum of errors. In other words, we want to determine alpha and beta, but at the same time, we want to minimize the total errors we are making. So that's the main, underlying theory for the regression analysis. And that's what we will do. Okay? So let's say the regression line is expressed like this: yi hat equals alpha plus beta xi. I represent the data points, right? So we define ei equals yi minus yi hat, and this is our error. And in order to minimize the errors, we got to have some sort of measures to take the summations of errors and so on and so forth. But we already learned that if we add all these errors, for example, E1, E2, all the way to, let's say, En, this can be 0. Why? Because sometimes these values are canceled each other. And therefore, this is not a good way. So we want to have square terms. In other words, we want to square the errors. And I want to take some, summations. In other words, from data point 1 to data point n, I take the summations of the squared errors. Then that's good, because that way I can actually minimize. I can minimize the sum of errors, sum of squared errors, and at the same time, by doing so, I want to determine alpha and beta in a better way, appropriate manner. Now, I want to think about this concept. What is the maximum error I will make? In other words, what is the maximum error I will make if we do not use the regression analysis? For example, suppose that I do not know about the regression analysis, so I do not know. I cannot apply this regression model to predicting the relationship between x and y. Then what is the forecasting? What is the forecasting I can make without anything like, for example, regression model? The simplest, let's say this is the simplest forecasting. The simplest forecasting without the regression model is taking the mean value. In other words, if I do not have any sophisticated methodologies to understand the relationship between these two variables, the simplest way, the simplest measure is to use the average line. Average line. In other words, if I do not have any, anything like regression analysis, the simplest way for me to make a prediction is the average line, the mean value. I take y bar. If I take the y bar as my prediction, what is the error? I can make errors like this. This is the error, this is the error, and that's the error, and that's the error, and that's the error. So when I don't have any statistical tools, the simplest forecasting I can make is the mean value. And therefore, yi minus y bar, that's the maximum error I will make. That's the total error I make. Let's say that's total error. Or I can say that that's my maximum errors. Maximum errors. I cannot make errors. I can make an error bigger than this. Okay? That's the maximum error I will make. The maximum error I will make. Then I will decompose this relationship like this. yi minus y hat I plus yi hat minus y bar. That's just a simple, equivalent formula, because I just add yi hat minus yi hat, so nothing changes. But something interesting we can observe, okay? And this is the error we can make, actually, this one. This one is that one. And then this one is another different types of errors. So now I want to take squares. In other words, I want to take a square so that I want to n yi minus y bar square, and I take the same thing. But it turns out that because of some of this statistical independence, what we will have is going to be something like this. You can actually show this happens. Square, and this one is going to be n yi hat minus y bar square. Right? What happens is that you actually take a square, and then you take the square and take the summations here, right? but because of some statistical independence, some of the cross terms are cancelled out, and then eventually we will have these three terms. yi minus y bar square summation equals yi minus yi hat square summation plus yi hat minus y bar squares. Because some of these interaction terms will go away. And then we call that as, this one is called total sum of squares, in other words, total errors. Okay, so what I will do is I will write it here, a verb, because I want to make sure that everybody sees what it is. So that's total errors. So we call that as TSS. TSS is total sum of squares. Total sum of squares. Total sum of squares. Or squared errors, or some sort of errors. And this one is called ESS. In other words, error. Error sum of squares. And this one is called RSS, which is called regression sum of squares. Okay, so this is a very famous result. In other words, total sum of squares equals error sum of squares plus regression sum of squares. And you got to understand what the actual forms of each one of these sum of errors. Okay? And then we remember that we have the measures R square. R square is nothing but RSS divided by TSS. In other words, R square measures regression sum of squares. In other words, the maximum errors we make, or the errors we can explain. This is somehow, we would just say that the errors explained by the regression model. That's the errors explained by the regression line. So that's RSS, and TSS is the total errors, and therefore R square actually means that proportion of total errors that can be explained by the regression model. Okay, that's basically R square. R square is how much of total errors I can explain with the regression model, and therefore the larger the R squares, the better. In other words, the larger the R squares, the larger proportion I can explain. The larger proportion of the total errors I can explain using the regression models. So that's the R square. Okay? And then I will compare this F statistics and the p-values related with F statistics together. Okay? So let me just go over our regression model. Let's say we have a basic regression model here. So why don't I go there? Okay, so let me just and I will rewrite all these things for you. So let's say we have white and projector. Okay, think about this one. This is our very simple regression model. And then we have our data set and go to the regression analysis and cost per hour, sales per hour. Okay, very good. So let's say that's what we already know. Okay, let me explain each one of these outcomes one more time. Okay, so we already learned that the TSS, total sum of squares, error sum of squares plus regression sum of squares, regression sum of squares. So let me go over this whole thing. When you look at this table, it says the ANOVA table, which is analysis of variance. ANOVA implies analysis of variance. Analysis of variance. And it says that explained, and we already mentioned that explained meaning that, let's say, yi hat minus y bar. These things are already known if we use the regression model. So that's explained. And unexplained is yi minus yi hat. That's not explained. That's not unexplained. That's not explained. In other words, that's unexplained. So when we say RSS, you see here square of sum of squares, and this one is RSS. RSS is regression sum of squares, and unexplained portion is called error sum of squares. Error sum of squares. So this one here. And therefore, what is it? Total sum of squares will be this one plus that one. Okay? So if you add them up, you will have the total numbers. Okay, let's see what's the total sum of squares. The total sum of squares is going to be, let's say, this is sum this one is this one plus C15. Okay, so that's 19,130. Okay, that's total sum of squares. Total sum of squares. Okay, total sum of squares equals error sum of squares plus regression sum of squares. And we said that R square is RSS over TSS. So that's R square. And then that means that what? TSS is 19,130 and RSS is 13,275. And then you will have this R square. Okay? So we're going to have R square there. And then another concept we should consider is the degree of freedom. Degree of freedom. And in this case, let's say we have n as number of data points, and k is the number of independent variables. Okay, if that is the case, when we say degree of freedom, this one is k. In other words, the degree of freedom for explained variance is k, because we have in this case only one independent variable, and the total sum of squares, the degree of freedom will be n minus 1, and therefore when we add the degree of freedom for RSS and degree of freedom for ESS, that should be equal to the degree of freedom for TSS, and therefore this is going to be n minus k minus 1. Okay, so degree of freedom is determined like this. First, total sum of squares. How we get this total sum of squares? We use one estimate. In other words, we take the average value when we calculate the total sum of squares, and therefore we use one data points when we calculate the mean values. So the degree of freedom will be n minus 1. And then the regression sum of squares degree of freedom is number of independent variable, and therefore the remaining degree of freedom should be n minus k minus 1. Okay, so if you add k plus n minus k minus 1, you will have n minus 1. So we have everything here. So sum of squares, as we said, the total sum of squares equals error sum of squares plus regression sum of squares. Very good. And with that, we are able to calculate this R square. And then if you look at here, mean of squares, how I calculate this one? This one is basically RSS divided by K, in other words, degree of freedom. And this one is ESS divided by n minus k minus 1. In other words, mean of squares is just the sum of squares divided by degree of freedom. So in this case, 13,275 divided by 1. So we have 13,275. And here, 5854 divided by 3. Then we will have 1951. So the mean of squares is just the sum of squares divided by degree of freedom. So sometimes we express this as M. This one is MSR, mean sum of regression, and this one we sometimes call MSE. In other words, mean value of sum of errors, or error sum. So we call this as MSR. This one is MSE. Now, the F statistic is nothing but MSR divided by MSE. MSR divided by MSE. In other words, you divide 13,275 with 1951, you will have 6.8. Okay. So now we are calculating all these numbers. You can actually calculate all these numbers, but StatTools do that for you. Basically, you identify the degree of freedom, and you take the sum of squares like this, and then mean of squares is just to divide the sum of squares by degree of freedom, and then F statistic is MSR divided by MSE. And using this number and some of this, using some F distribution, you will calculate the p-value here. And we already said that null hypothesis in this case, the regression model, the regression is useless, for example. Okay? So null hypothesis is that the regression model is always useless. So the smaller the p-value, in other words, in this case, p-value is 0.07, 0.08, something like that. So we would just say that at the significance level of 10%, we can reject the null hypothesis, but at 5% or 1% significance level, we cannot reject the null hypothesis. So the regression model is acceptable, but not as good as we expected. And now, as you can see, there is a slight difference between the R-square and this F statistic. For example, R-square is determined by RSS divided by TSS. In other words, out of these total errors, how much I can actually explain with my regression model. That's R-square implies. That's what R-square implies. On the other hand, F statistic. What is F statistic? F statistic is MSR divided by MSE, which is what? Let's say this is RSS divided by degree of freedom, and ESS divided by n minus k minus 1. So you see, we said that R square as well as F statistic says something about the validity of the regression line as a whole. But as you can see, the measures are slightly different. In other words, the numerator is similar. The numerator is RSS, the same, regression sum of squares. But the difference is denominator, right? R square, we divide this RSS, regression sum of squares, by the total errors, whereas F statistic, we divide this regression sum of squares by error sum of squares. So, you know, this is about how much I can explain, how much of the total errors I can explain with my regression model. That's what R square measures. And what about this? Compared with unexplained variance, how much I can explain. Okay? So these two measures seem to measure the same thing, very similar thing, but they are not exactly the same. That's why sometimes there is some discrepancy between these two. In other words, sometimes we might have some low values and bad R squares, but it's possible for us to have a good, very strong p-value based on the F statistics. Okay? So if it's too complicated, you can forget about the details, but I just want to make sure that you remember that both R square and F statistic tell us about the overall validity of the regression line as a whole. In other words, this will tell us about whether the regression line itself is good or bad overall. And this one also tells us about whether the regression line is good or bad. But they are not exactly the same. Because this one tells us about out of these total errors, how much I can actually explain. How much I can explain with my regression model. On the contrary, the F statistic says something about compared with the unexplained errors, how much can I explain? Okay? So there is a slight difference, but I think that the difference is not that big. But I would say that it's not absolutely true, but if I can give you some rule of thumb, in practice, people want to use R square. If you go out in the practice or the consulting company, they usually talk about R square, whether R square is good or bad. But in academic research, we usually want to pay more attention to this F statistic. Okay? So that's kind of a rule of thumb. That's not absolutely, theoretically true or something like that, but still that kind of a rule of thumb. Now we know everything here, right? So we know how we get this coefficient. But I didn't talk about the equations, but given this coefficient, the standard error is something we already know from our confidence interval hypothesis testing, and t-value is just a coefficient divided by standard error. If you divide 57.1 by 50.4, you would have a 1.13. If you divide 0.93 by 0.936, you would have a 2.6. And this p-value, t-value, and you use, let's say, t dist, for example, RT or whatever, you can use Excel function and you will get the p-values. And then you will see that, okay, this is acceptable. I mean that you can use the rule 1%, 5%, 10%. But sometimes you don't need to use this significance level. You just can say that, okay, p-value is 0.08. So if I say that I want to reject the null hypothesis, in this case, null hypothesis is beta is 0. In other words, there is no relationship between the independent variable and dependent variable. If I want to reject that, how much confident am I? I'm confident at 92%. In other words, I'm confident at 1 minus p-value. If I reject this null hypothesis, I can ask a question: how confident am I? How confident am I when I say that I want to reject this null hypothesis, and therefore there is indeed a relationship between independent variable and dependent variable? How confident am I? I'm confident as much as 1 minus p-value. So the smaller the p-value, the more confident I am, right? So in this case, we want to have very small p-values. And I talked about how we can reach the same conclusion by looking at this confidence interval. But if it's confusing, just forget about this. You don't need to understand this one, okay? If it's confusing, just forget about this. It's useless, okay? So just forget about it. And focus on the p-value. So you have to tell me, is there the relationship between the independent variable and dependent variable? You can tell me about that by looking at the p-value only, okay? The smaller, the stronger. Forget about how we get this p-value, just, forget about it. As I said, in this course, regarding the regression analysis, your task first, set up the regression model based on your managerial judgment. Second, using the star tools to derive this report. Third, show me how you interpret all these numbers. Okay? The first thing is that you have to reconstruct the regression line. In this case, y equals 57 plus 0.93x. So you first construct the regression line, and then tell me about overall fitness, overall goodness of this regression line. You probably talk about R square and F statistics p-value. And then you need to talk about whether indeed there is a strong positive relationship or strong negative relationship between independent and dependent variable by looking at the p-value associated with the regression coefficient. And that's it. And then the next step is your prediction, how you can predict. In other words, our regression line is y equals 57.1 plus 0.93x. Okay? Then let's say, what if there are 10 cars passing by, 10 cars pass every hour? What is the expected sales? What is the expected sales? Okay? That's prediction. The reason why we have this regression line, is I want to make a prediction. So that's our regression line. And then the question is, what if there are 10 cars pass by every hour, what is the expected sales? How can I answer the question? How can I answer the question? Sumi, how can I answer this question? Can you answer this question? This is the regression line, and my question is, okay, that's good. I have a good relationship. Then the question is, what if there are 10 cars? What if there are 10 cars passing by? What is the expected sales? Can you answer the question? So where I put 10 here? X. Okay? So that's our prediction. That's a statistical inference. So then it means that our expected sales is going to be 57.1 plus 0.93 times 10. Then 57.1 plus 9.3, that's going to be 66.4. So that's prediction. That's the prediction we're going to make. And that's our goal, actually. Our objective is to making a prediction. Okay? Right. Then I need you to explain this adjusted R square. I can talk about some formula. I can talk about some equation. But rather than that, I just want to give you conceptual understanding. Conceptual understanding. We know that in this model, we have only one variable, one independent variable. If we add one more independent variable, R square will increase. R square will improve. Whenever you add one more independent variable into model, R square can never go down. Right? Okay, for example, let's say I have y alpha plus beta 1 x1, and let's say alpha plus beta 1 x1 plus beta 2 x2. So as I add one more variable into the model, R squares never go down. Why? Because if it is true that x2 is useless, then we can always put this beta 2 equals 0. Nothing lose. We have nothing to lose by adding one more variable, because whenever it's true that the extra independent variable is meaningless, then we can just put beta 2 equals 0. And therefore, okay, what happens is that whenever you add one more independent variable, let's say that's number of independent variables, as you increase one more independent variable, what happens is that R square never go down. It never go down. It goes up or it stays the same. But sometimes we have to ask question something like this. How many independent variables I want to have in my model? How many independent variables I want to include in my regression line? So you cannot go on forever. In fact, as you increase one more variable, you somehow lose your degree of freedom. So what happens is that that's your adjusted R square. That's your adjusted R square. As you increase number of independent variables, although the R square itself never go down, but adjusted R square, meaning that the R squares adjusted by the degree of freedom. The R squares adjusted by some form of degree of freedoms. So sometimes, even if the R square increases, even if R squares increases, the adjusted R squares will look like this. And then the question is, how many independent variables should we increase in the model? Okay, so that's our optimum. That's our optimum number of independent variables, right? So R square, the original R square never go down. But as we increase the number of independent variables in our regression model, adjusted R square will go down when the additional independent variable is actually useless. Then the adjusted R square will go down. And therefore, when we have a multiple regression model, we can always compare different models and see whether it's better for us to increase one more independent variable or not. All right. So now we understand everything. Now we can calculate every number in this regression report. Okay. Very good. Any questions so far? Well, actually, I gave you this, 1 or 2 page lecture note in the Word format about this, error, sum of squares, and so on and so forth. But again, if you feel this is a little bit confusing, that's fine. Okay? I explain this because I want to make sure that you have some understanding about the logic behind all these, numbers. But since we now have some, at least the basic ideas about the logic, basic ideas about the theory, it's time to forget about it, okay? So you just to forget about it. So what is important is, what does it mean for us to have this p-value? What does it mean for us to have this p-value? What does it mean for us to have this R square? What does it mean for us to have this adjusted R square? Why we are interested in this adjusted R square, and so on and so forth. And then, how can I make a prediction? How can I make a prediction? Once I have this regression model, I want to make sure that I can make a prediction. Okay, very good. So nothing so difficult, nothing so complicated, and everything is straightforward. So now we understand that what is important is not technical understanding. What is important is not technical application. What is more important is your creativity, your managerial judgment to set up the model, to find out the appropriate relationship between variables. Finding out the exact regression coefficient, you don't have to worry about that because the star tools will do that for you. Okay, very good. So I think that this one, and then we talked about the possibility that whether we have some, highway exit or not, then we can convert. Okay, that's what I mean by your creativity. you start with the relationship between sales and number of cars, but after that, you realize that you are interested in another more advanced model, because you realize somehow whether the store is near the highway exit might affect the relationship. And then if that is the case, then you have this one, and then this is a categorical variable, and therefore I need to convert this variable into something that can be understood by Excel, and therefore I convert this into dummy variable. And dummy variable says that you can put this, this is 1, 0, 1, 0, 1. Okay? And then you define this as another data set, and you have regression analysis. You work with your second data set, and then sales power, okay, very good. So now, as you can see, the regression model improves a lot. R square increases, and I'm sure that the adjusted R square is improved as well. Adjusted R square is also improved as well. In this case, adding this near highway exit is a good choice. Good choice. Okay, and then I think that you also have this data. This data says that this is about a product which has some characteristics that are affected by some other variables. So I think that when we have this model, our idea our initial judgment, managerial judgment, is that, okay, let's say we have a little bit larger. Okay, so I think that my guess is that, okay, our sales somehow related with let's say promotion and also B2 advertising and somehow the economic index, economic condition. Okay, so you go to status, data set, integration analysis, and I want to have my sales and promotion, advertising, and index. Okay, then that's what I have. In other words, first I have to write down the regression line. I have to write down the regression line first. What is my regression line? Y equals 883.5 plus, okay, let me see, this one I can make it larger, and 5.2 times promotion plus 3.11 times advertising minus 5.63 index. Okay, Okay, so the first thing that you have to is write down the regression line. Write down the regression line. In other words, my sales is the constant plus 5.2 alpha beta 1 times promotion plus beta 2 times advertising minus beta 3 times index. And once you write that down, you might go to R square and p-value and saying that, okay, the R square is 0.6. It's good, relatively good. But what is more relevant is this p-value, and it is very small. It is smaller than 0.01. Therefore, I would just say, okay, this regression model as a whole is good. It's strong. Because I can reject the null hypothesis which says that the regression model is useless. I can reject that null hypothesis quite confidently. My confidence level is larger than 99% in this case, okay? But what is more important is to look at these p-values, and you forget about p-value for the constant. It does not have any meaning. It does not have any meaning, okay? P-value for the constant does not have any meaning. But now we look at these p-values for the regression coefficient, and then the null hypothesis. For example, let's look at this promotion. The regression coefficient is 5.2, and then the p-value is 0.0002. It says that if I reject the null hypothesis, in this case, null hypothesis is beta 1 equals 0. Beta 1 equals 0. That means that there is no relationship between promotion and sales. But now, if I reject that null hypothesis, in other words, if I reject that there is no relationship between promotion and sales, if I reject that, how much confident am I? I'm almost 100% confident. Because my confidence level is 1 minus p-value. And in this case, 99.9 is my confidence level. So this is very strong. And that means that I can reject the null hypothesis which says that beta 1 equals 0, which says there is no relationship between promotion and sales. I can very much confidently, perfectly confidently, I reject the null hypothesis. What about this? This is also strong. This is smaller than 0.01, and therefore I confidently reject the null hypothesis, and therefore the other side of that statement is that there is indeed a positive relationship. There is indeed a positive relationship between advertising and sales. There is indeed a positive relationship between promotion and sales. And now we have negative regression coefficient for index, and I would just say, okay, there might be negative relationship between the economic condition and sales of this particular product. And I said this is inferior good, meaning that when people have more money, they used to reduce the consumption of the product. If that is the product, then we call that as inferior product. And this might be negative relationship between these two. But when I look at this one, the p-value is not good. And in this case, what I can say is, but this is not terribly bad either. If the p-value is 0.3, 0.4, then I would just say that's completely useless. That we cannot say anything about the relationship between this variable. But this is 0.15, which is, if I reject the null hypothesis, probably my confidence level is 85%. So actually, when Nayeon asked some question, I said that if p-value is larger than 0.1, you can just throw that away. You can do it. Or sometimes you might say that, okay, this is not strong enough, but somehow I suspect I cannot say the relationship between economic condition and the sales of this product is negative. I cannot say that, but somehow I can suspect there might be some negative relationship, but I'm not sure. I cannot state that, but somehow I can suspect. That's what I can say, okay? But again, there is no theory that says that p-value 0.15 is useless. It's useless in a sense. But I would just say that because in an economic sense, it sounds interesting. It seems making some sense because this product is a soup, chicken soup, the sales of a chicken soup. So when people have more money, they usually do not buy this chicken soup in can. This is a Campbell soup, chicken soup. So usually people when, do not have enough money, they buy this canned food, right? So in a sense that I think there might be some relationship. Okay. Once you have this initial regression model, you think about, is this the best I can do? I mean, is this the best model I can think about? So once you have your initial model, you have to think about whether I can improve this model a little bit further. And then you have to think about some logical relationship. Is promotion the same thing as advertising? What do you think? Are these same thing? Heading. You need to have your nameplate, right? So is promotion same as advertising? What do you think? What's the difference? Are they different? What is the example of promotion? You go to the mart and there is promotion. What is it? Sometimes the promotion. You buy one, get one free or something like that. That's promotion. Okay? What about advertising? What is the advertising? You can see all these commercials in TV and radio and, those are the advertising. So promotion and advertising are two important marketing tools, but they are not exactly the same. They are not exactly the same, right? Okay, Mino, you also need your nameplate, right? Okay, so I said that advertising and promotion are different. What about their impact on sales? What do you think? Do they have the same impact, the promotion and advertising? Has more, when you look at this one, forget about this magnitude. What do you think the long-term impact of a promotion and long-term impact of advertising? In other words, promotion is about, buy one, get one free or something like that. Whereas advertising is commercials in the TV and the radio. So do you think there might be some difference in terms of a long-term impact of each one of these tools? What do you think? You? Wonjun, what do you think? Are there any long-term differences in terms of a long-term impact?
I think so. If long-term, it could be a bit different.
For example, can you guess the difference?
Because the p-value of promotion is smaller than advertising. So the promotion effect is more powerful.
More powerful. Currently, okay? Currently. Okay, let me give you some additional information. Let's say promotion is buy one, get one free, okay? Let's say when you go to the mart, you didn't plan to buy a certain product. because you said you think that you're going to buy it next month or next quarter. But when you arrived at the mart, there is big promotion going on. Buy one, get one free. So even if I plan that I'm going to buy that product next quarter, but when I saw the promotion, it's tempted, right? It's very tempting. So I change my mind, so I buy that product. Even though I planned to buy it next month or next quarter, but because of this promotion going on, I buy it today. And because I buy it today, I'm not going to buy it next month or next quarter. Because I buy it today. I buy it in an earlier period. And therefore, somehow I do say that the promotion might have some negative impact on the future sales. Promotion has positive impact on the current sales, the sales right now, but it might have some negative impact on the future sales, the sales in the future. On the other hand, think about this advertising. Advertising is some commercials. So when I watch TV, when I watch the commercial today, I don't memorize everything. But if I'm exposed to the same commercials over and over again, I somehow memorize it. And then that memory will last for a long time. So if I am exposed to that advertising today, that memory will resurface next month, and therefore next month I might be willing to buy this product because I remember this advertising. So although the current impact of promotion as well as advertising is positive on the current sales, my guess is that the long-term impact might be different. There might be some differences in terms of a long-term impact. In that case, how should I change this whole thing? Okay, so that's something I want to worry about. I want to think about. In other words, I would say this quarter's promotion will have some impact on next quarter's sales, and this quarter's advertising might have some impact on the sales in the next quarter. And if that is the case, I have a new regression model. For example, here, sales is going to be A plus B1. Okay, let me do the same. Okay, I add some regression models here. So let's say copy it, paste it. But this is not the whole thing. I want to add some additional variables. In other words, B4 times previous promotion, previous period promotion, plus B5 times previous advertising. That's my new model. That's my improved model. Okay? The whole thing of this regression model is that you improve your model over time. You start with the simple model and you learn the regression, and then you understand all this relationship, and then you think about, you ask a question, you ask yourself, is this the best? Is this the best regression model I can come up with? Are there any extra variables I somehow miss? Can I include some additional variables? Or can I improve the model so that I have a better relationship, better, let's say, validity large validity of the regression model? So you have to ask a question. And then I say that, okay, after thinking about all this promotion and advertising and the differences and their long-term impact, I somehow ask myself, okay, somehow promotion has current impact. Promotion has an impact on the current sales, but somehow the promotion will have impact on the future sales as well, next period of sales. In this case, we call these variables as time lag variables. Okay? Time lag variable. In other words, somehow I need to make sure that this one affect next period of sales. Okay, so let me say. So sometimes when you have a new model, you have to create extra variables. In other words, here, let's say now this one is promotion at T, current period. This one is advertising for current period. And now I have promotion T minus 1. In other words, previous period promotion. And this advertising T minus 1. But we do not have these variables. We do not have these variables. We do not have these variables. How can I create these variables? We already have this one. And therefore, somehow, what I'm saying is that promotion in quarter 1 will have some impact on the sales on quarter 2. Promotion in quarter 2 have some impact on sales on quarter 3, and so on and so forth. So now, I can see that how I can convert this variable into this one. I just copy it and then paste it. So what I will do is I will just copy all this and then I paste it here. Okay? Okay, I think that somehow I have to change this thing a little bit. This is not the case, because what I have to do is, let me see. Copy and paste. Okay, that's more appropriate. In other words, my sales in quarter 2 will be affected by promotion in quarter 2 and advertising quarter 2 and index quarter 2 and also my promotion in quarter 1, right? And I do the same thing. So what I will do is I copy this and I paste that here. Then what it says is that my sales in quarter 2 will be affected by advertising quarter 2 and also advertising quarter 1, because I believe that the advertising has some long-term impact as well. And by doing so, what happens is that we lose these data points. So let's say I want to put it here. And I needed to delete this one. Okay, so I have now this, and then let's say 24 2. Okay, so I go to regression analysis. There's 2 sales, promotion, advertising index, previous. Okay, very good. What can you tell? I make the regression line stronger, right? Because that's the previous regression. R square and adjusted R square is there. And this is the current regression. So as you can see, the R square improved significantly, and also the adjusted R square improved significantly. Therefore, by adding these two variables, we are actually making the regression line much stronger. And the first thing we have to do is we need to the regression line sales is 757 plus 5.9 promotion, current promotion plus 2.3 advertising, current advertising, minus 4.5 index, minus 3.2 previous promotion, plus 2.6 times previous advertising. Okay, very good. So now we see the regression model is great. And when I look at p-values for the independent variables, they all look much better, except for this index. But still, index is seems okay now because it's almost 90% confidence I can have when I reject the null hypothesis saying that the coefficient is 0. What is striking is what? This one now, negative. It's not just negative, very strong negative. So what does it tell? Compare this one. This one is negative, this one is positive. Both are very strong. What does it mean? It means, indeed, my guess was right. My guess is right. Promotion has positive impact on current sales, but promotion has negative impact on the future sales. That's obvious. Because people buy things, when they see a promotion, they usually buy things ahead of time. So they buy things which they want to buy next quarter. But because of promotion, they buy it today. That means that the customer will not buy the product next time. And therefore, promotion actually has some impact that you purchase things earlier. It's not creating new sales. So promotion is not creating new sales. It actually changed the timing of the sales. On the other hand, advertising has a positive impact, positive current effect, and positive time-lagged impact. In other words, advertising has a long-term positive impact as well. In other words, if you spend some money in advertising, people remember your product, people remember your service, and they will buy those products, those services in the future. So we have a great outcomes. As I said, regression analysis is a very powerful tool you can use. And then we learned, while we considering all this, we learned a lot. First, we talked about how we can use this dummy variable. And then now we learn how to use this time-lagged variable. And sometimes why it's important, because some decision does not only have a current impact, but also has some long-term lasting impact. So we can actually incorporate that feature into our regression analysis. So the first thing is you come up with a very nice, very strong regression model, conceptual model, and use the STAR tools to the regression analysis. And then you reconstitute the regression line, and then go over this R-square and F statistic. Especially pay attention to this, and this says that the regression model as a whole is very good, very strong. And then you need to look at these p-values for these independent variables. And I would just say that most of these p-values are very strong, and the signs of coefficient actually very strong. And then you need to reinterpret what it means. For example, what it means to have this promotion, what it means to have this advertising. Okay, so that's the overall procedure. Again, I want to thank you for coming this early today, and I need one more cooperation from you on Wednesday. Okay, so I'm going to have a class on Wednesday 8:30, and then next week Monday we're going to have an exam, which is focused on the regression analysis. And then next Wednesday, happily we're going to have a break, right? Holiday. So we're not going to have any class. So go over this regression analysis, and on Wednesday, I will work on this exercise problems with you, and I will give you more details about the exam on next Monday. Okay? Thank you again, and have a great day today. All right? So I will see you Wednesday.